Hello, everyone. Thank you very much for attending our tech talks today. We are extremely excited and honored to have Dr. Chen from University of Pennsylvania to give us a talk about EHR and data integration. But before I introduce him, let me mention some housekeeping issues. So we will continue to extend our CME credits for our tech talks and ID series presentation. We will distribute now the information via email to all of you who have registered for today's event. If you did not register prior to today's talk, you can still obtain CME code information from Lisa Maturo at ChristianaCare. Her email address is lisa.m.maturo@christianacare.org. We will have a tech talk on August 6th. Dr. Ryan Pollick from University of Delaware will talk to us about latent class analysis. And then we'll have an ID series. So the tech talks are on Thursdays, monthly, and the ID series are on Fridays. So the next ID series will be on September 11th, and that will be Dr. Regina Wright from University of Delaware. We'll talk about neighborhood disadvantage, brain health, and neurocognitive function, a cross-sectional analysis of interrelations among cognitively normal older adults. So again, I'm really excited that we have Dr. Chen today to give us a talk about EHR and data integration. So Dr. Chen is Associate Professor of Biostatistics and Director of the Computing, Inference, and Learning Lab at University of Pennsylvania, where his research focuses on statistical inference, evidence synthesis and data integration, electronic health record data, drug safety, reproducibility, privacy, and high dimensionality of biomedical data. He's had multiple awards along the years. Among them was elected Fellow of the American Statistical Association in 2020. He has a very long list of peer-reviewed publications and has been continuously funded by NIH, PCORI, or AHRQ. So again, we are really honored to have Dr. Chen. Thank you so much.
Thank you, Claudine, for inviting me, and thank you for the nice introduction. So it's really my great pleasure to share with you what we have been working on. So let me first share my screen. So can you see my screen?
Yes.
Okay, great. So today, the topic of my talk is expanding the reach of EHR through data integration. So for those of you who don't know what EHR is, EHR stands for Electronic Health Record. So I will talk more about it in the later slides. So all the related publications are available in our lab website. Our lab website is called pencil.org. So pencil stands for Computing, Inference, and Learning Lab at UPenn. So you can also feel free to contact me through Twitter, and my email address is provided here. So as many of you know, we are in this digital era. So EHR data is becoming more and more popular. So basically, EHR data is a digital version of medical records, and it contains a lot of information, including lab tests, medication, physician's notes, and many other information. So recently, people start to ask questions, how to fully utilize the EHR data, and how can we translate the EHR data from data to knowledge, and from knowledge to insight, and also we want to use the data to inform our clinical decision making, and also inform the future research agendas. So in the past few years, we have been working on this general topic of, we call it EHR data plus X. So X stands for many other things, which I will explain. So we worked on all these 4 areas. The first area is, we call it the EHR plus EHRs, because for many conditions, actually, the data from one hospital is not enough. So we want to integrate data from other hospitals in a privacy-preserving fashion. And this is particularly important when we study rare diseases, and often the case, you only have very few number of cases in one particular hospital, and the rare diseases can be also very heterogeneous. And another important scenario is to study the drug adverse event. It's, as we know, adverse event for medications, especially those medications post-marketing, are relatively rare and can be extremely rare. Using data from one hospital is not sufficient. So we do need institute collaborations to combine data together. So the first part will be the topic of this presentation. And we also work on other areas like EHR data plus genetic data. This is also known as biobank. So we have been working on the UK biobank data, which has 500,000 patients with their EHR data linked with their genetic data. And more recently, we are working on EHR data plus imaging data, and trying to, by linking those rich, large data sets, we are hoping to gain new insights about causal relationship and associations. And also, EHR data plus external knowledge is another very powerful combination. So since we have been working on handle measurement errors and missing data issues, those are well-known issues due to the low quality of EHR data. Especially EHR data is not collected originally for research purpose. It's really so there are lots of issues with suboptimal quality of EHR data, and we are also working on combining EHR data with national vaccine or drug adverse event surveillance data. So those are the areas. And for the limited time, I'm going to focus on the first one. We have some interesting ideas and results to share with you. So let's focus on this EHR plus EHR. So the framework we are developing is called the Privacy-Preserving Distributed Algorithm. We also call it PDA. In the past several years, we have got exposed to many interesting research consortium. One of the largest consortium we got involved is this ODYSSEY, stand for Observational Health Data Science and Informatics. So this is an international effort initiated by Columbia University and Johnson & Johnson. So quickly it becomes very popular platform for collaboration. As you can see, there are multiple countries, actually more than 20 countries involved in ODYSSEY now. And the ODYSSEY consortium actually covers the EHR data from about 300 million patients. So that's a huge, that's a tremendous amount of resource and that people can use to advance research. As the way the data was saved are still in the distributed fashion. So basically, there's no one who can pull all the data together in one place. So the data still sit in their individual countries and individual hospitals, but people can initiate a research topic and ask those people, the data owner, to contribute some summary statistics which do not contain patient privacy to help answering research questions. So that's the model for ODYSSEY. And also the PCORI has in the past 10 years has also funded a number of research consortium. They call it PICONet. So PCORI is part of the national funding mechanism originated from Obamacare, and they have been funding more than a dozen PICONets. So over here, each of the research network stand for a collection of research institutes who are sharing data together, either distributively or or pulling the data together. So in the past few years, we have been working with PISnet, which is led by Children's Hospital of Philadelphia, CHOP, and they have data from 8 children's hospitals. And also, we have been working with One Florida. So they cover about 60% of the residents in Florida. They have about EHR data from about 40 million patients. So all those resources actually highlighted the importance of multi-center study. So why do we need multi-center study? Let's step back. So as a statistician, we know multi-center study will lead to larger sample size. And typically, if you do things right and make reasonable assumptions, and larger sample size will give us greater statistical power. It can also offer opportunities for us to study rare events and can potentially lead to more generalizable research findings. And from collaboration point of view, multi-center study can also bring together investigators who share and leverage resources and expertise and ideas. But what are the barriers? The primary barrier is patient privacy. It's difficult and logistically challenging and to share patient-level data together. And also the communication cost, the time, effort, manpower, storage, it can be also another barrier when we have multi-center study. So that's actually, those are the challenges are actually the reason to motivate our research in the last few years for this particular topic. So from statistical modeling point of view, if we ask the fundamental question, do we really need to share patient-level data? So the answer is that it depends. So suppose you are fitting a linear regression, just a simple linear regression, y regress on x, and you have data distributively stayed at different hospitals, x1, x2, x3. This is called the design matrix. When you pull the data together, we know how to fit this model, and this is our familiar ordinary least square estimator. So dated back to 2006, is actually the original idea was actually much earlier. The people have shown that this calculation can be done in a distributed fashion, meaning that this design matrix can be calculated within each hospital. Like this hospital, you can calculate x1 transpose times x1. And suppose you have 10 predictors in your regression model. So this will simply be a 10 by 10 matrix. And then the second part, this is x1 transpose times y1, which is a 10 by 1 vector. So this simple equation basically is suggesting that we only need to communicate a p by p matrix and a p by 1 vector, and then you will actually get identical results as if you pull all the EHR data together. So this actually opens a window of trying to do the operations in a distributed setting rather than a pooled data setting, which is logistically very challenging. So what are the current state of art? So roughly speaking, we break the current methods into two categories. One, we call it the lossless, meaning that you will obtain the identical results as if you pull the data together. So as I just showed you, for linear regression, you can do it in a distributed setting, the fashion. But for nonlinear regression, like logistic regression or time to event analysis, like Cox proportional hazard model, it's more complicated because there's no clean closed form solution, and you have to do it iteratively. So the key idea in these two papers was that for each Newton-Raphson updates, it's essentially a weighted least square or something alike, then you can distributively calculate this using the idea from linear regression. So that's the key idea. So the advantage here is that you would actually get the identical result, meaning that it's lossless, but the disadvantage is that you need multiple rounds of communication. So this is actually a very big barrier because for settings like PCORI or especially Odyssey, there are many international collaborations. It's just very difficult to have multiple communications to update the parameter estimates. So the Another a group of method, we call it one-shot. So the one-shot emphasizes the communication efficiency. You only communicate once, just like a meta-analysis. Or if you are familiar with machine learning approach, it is essentially a divide and conquer. So you ask people to do some task, and then ask them send the result back, and you are going to just combine them together. So meta-analysis is probably the most popular one-shot approach. And also, recently there are distributed PCA, distributed LDA, and so on. There are many recent interests on this one-shot algorithm. So the one-shot algorithm that we are particularly interested in is this surrogate likelihood approach, and it's from a paper published by Michael Jordan and his colleagues in 2018 at JASA. And then since then, there has been lots of interest using this surrogate likelihood approach. So having reviewed the existing approach and the research gap, let's talk about how to design our method. So we aim to enable more efficient information sharing. So we want to emphasize accuracy, safety, and the communication cost. We want it to be fast. So let me just first introduce you the data structure. So in many consortium, we also call it distributed research networks. The data is typically stored at different hospitals. But a very interesting setting, I think ignored by some meta-analysis or IPD meta-analysis, was that we actually have, as an investigator, for example, I work at UPenn, I do have access of individual patient level data at Penn Medicine. But on the other hand, other hospitals like Delaware and and other hospitals, Columbia and those hospitals, they are willing to collaborate, but they cannot share patient level data. So we are in this hybrid situation that we have partial access of individual patient level data at a local site. On the other hand, other places are willing to share their aggregated data. So this is the data structure. So with this in mind, I'm going to introduce you this OLL method, and this is OLL stands for one-shot distributed algorithm for logistical regression model. So from now on, I'm going to get into some technical detail with Greek letters, but I hope to keep the discussion and the insight at a high level. So basically, this is the combined likelihood function. It's simply log likelihood function when you have from the data from k different sites. So for simplicity, let's assume each site has n subjects. So this is simply the logistical regression from k different clinical sites. Each site has n observations. And now we can also have this local likelihood functions. Similar likelihood function can be constructed using my data access at UPenn. So this is like the likelihood function from all the data pooled together. But obviously, we don't have this likelihood function to work with because we cannot have the pooled data. So the key question is, how do we borrow aggregated information from other sites, those collaborating sites, to help this local likelihood function to approximate the combined likelihood function? So that's the key idea. So the answer is actually ridiculously simple. The answer is to basically to use tele expansion. So here is the idea. So use initial value beta bar. For example, you can train your logistical regression model at your local site, and you do a tele expansion for the combined likelihood function at this initial value. And similarly, you can do a tele expansion for the local likelihood function around this initial value. Just for simplicity, we are going to only do tele expansion for to the first order. We're going to put all the second order and above in this bracket. Okay. So the idea is that we can use the idea from this Michael Jordan and his colleagues paper is that we can use this high order term, those terms in green box to replace those high order terms in the red box. So you can do some simple mathematical manipulation So just move this to the left hand of the equation, and then use this green box to replace the red box, basically adding this term with this green box and reorganize the term. You end up with this so-called first-order surrogate likelihood function. So this likelihood function, if you observe it, is essentially based on the local likelihood function, but you replace the gradient of the local likelihood function at the initial value by the gradient of the combined likelihood function at this initial value. So that's the key idea. And those gradients. Another idea here is that this gradient of the combined likelihood function can be calculated distributively. Basically, you can ask each hospital to send you this gradient of their local likelihood evaluated at this initial value. So that's the key idea. And later on, I can show you how powerful this idea is. And it turns out that this will give you almost identical results as if you pull the data together. So similarly, if we want to further increase the approximation accuracy, you can do second order Taylor expansion, and then you put a higher order together. So you can have a second order surrogate likelihood function, and those calculations are no more than some basic algebraic manipulations. So now with those two surrogate likelihoods, we have first order algorithm, we call it OLL 1, and the second order algorithm, we call it OLL 2, which is basically the maximum of the log, maximum of these surrogate likelihood functions. So as I said, the initial estimator can be an estimator from a local site. So now let's take a look at the algorithm. So first, you use your own data to train a model. You can do whatever model selection you like, and settle with a final logistic regression. You get your regression coefficients, data bar. And then the second step, you send this initial value to other sites. And then you ask those sites to calculate a summary statistics. Essentially, this is a gradient of their log likelihood function for logistic regression evaluated at beta bar. So this is simply if you have 10 predictors, this is simply a 10 by 1 vector to be sent back to the local site. So then you are going to use this 10 by 1 vector to modify your local likelihood function. You get this surrogate likelihood function. Then you maximize this surrogate likelihood function. You do this optimization. You get your augmented, updated estimator. This is your new estimator. So there are some theoretical guarantees, but basically we can the theory is that we will get identical efficiency, the same efficiency as if you pull the data together and fit a one logistic regression. Okay. So let me demonstrate this idea in a real-world setting. So we took the data from Penn health system. So we studied an interesting question. So we consider the medical exposure, 100 most common medications prescribed during pregnancy, and we study the association of those medications with their pregnancy outcome. We have two outcomes: normal pregnancy versus fetal loss. Okay, and so what we did was that we cut this European health system database into 10 pieces, and then we use 10% of the data. We pretend that this is our local data. We only have the access to the local data, and the remaining 90% we cut in 9 pieces randomly. Now we have 3 estimators for this setting. One is obviously the gold standard estimator. We just feed a logistic regression using all 35,000 patients' data. We get this pooled estimator. So this is the gold standard. we also have the local estimator. Suppose I only have access of 10% of the data. This is a local estimator. And the OLL estimator is to be compared with both estimator, which use the individual patient level data in the local sites and also use aggregated data from the sites from 2 to 10. Okay, so here is the main results. So in the x-axis, we list all the 100 medications, and the y-axis lists the odds ratio. So all the medications were ranked by odds ratio from largest to smallest, between estimated from the pooled estimate. So over here you can see there are 4 estimators. One is local estimator, the second is pooled estimator in green. We also have OLL 1 and OLL 2, stand for first order and second order OLL. So if we zoom in, for example, this particular part, you can see here the local estimator basically is quite different from the pooled estimator. So this is associated with larger uncertainty because you only have 10% of the data. But on the other hand, the OLL 1 is fairly close to the pooled estimator. It's fairly close to the green one. But if you are willing to use a second order algorithm, you can see the purple one are actually very close to the green ones. You can almost hard to see the difference between the green one and the purple ones. This is suggesting that the second order algorithm, OLL, can give you a very good result and can avoid the data sharing. Okay. We are also interested in the inference, the confidence intervals. So it turns out that the OLL 2 overlap with the pooled estimator very well from this figure. So let's just recap what we have covered. We talk about the importance of integrating EHR data. We talk about this first order OLL algorithm. We also talk about another message is that by incorporating the second order information, the OLL 2 can also improve the accuracy. So now I'm going to talk about another outcome that is very, very important in EHR data setting, the time to event outcome. So logistic regression is typically used in cross-sectional studies and sometimes in longitudinal studies, but it does not directly incorporate the temporal information in EHR. So one of the strengths of the EHR data is that you have all the temporal information, temporal ordering. People take the medication, and then certain time, a few months later, this person has another event. So we have this temporal ordering and the time information. So this motivates us to further extend our model to time to event analysis. So this is very important in pharmacovigilance studies and in many other studies, risk prediction modeling and so on. So recently we published this second paper. We call it ODEC, stand for one-shot distributed algorithm for Cox proportional hazard model. So we the idea is that we can still use the surrogate likelihood approximation to build our algorithm, but there are some new challenges. The first challenge is that if you observe the log partial likelihood function, you can see here this risk set at a particular time point actually involves the data from all the sites, clinical sites. So the combined likelihood function cannot be simply written as a sum of individual likelihood function. So this is different from before. And as I said, the denominator involves data from all sites. So in our paper, we use some technique to get around of this, and you're welcome to read our paper, which I will talk about in the end of the talk. And so I'm going to show you the algorithm first. So the algorithm for ODEC is actually one more communication than the OLL. So basically, the step one So we ask people to do the initialization. So you fit an initial model, you get the hazard ratio estimate from Cox model. And you also need to send those unique event time. So if you have the event happened at a certain time, you need to organize a set. And you need to send those event time to the lead data site, and then to get a collection of all the event time. And also you need to share some intermediate results for the reconstruction of the surrogate likelihood function. So with those information, you can get the local surrogate likelihood estimator, the beta tilde. And another feature we added in this ODAC is that sometimes people may ask, which institute should serve as a lead institute to construct the surrogate likelihood function. So here we offer the option that all the sites can take lead in turns. Basically, the site 1 can serve as can get a surrogate likelihood estimator. Site 2 can also do this, and so on. And after that, we can have one more step called evidence synthesis. We can calculate a weighted average of all the estimators. Okay. So let's take a look at some simulation results, and which is actually very promising. And we simulated the setting of using data from 10 hospitals. We consider different settings. Each hospital has 1,000 patients. Also, we can have situations like 5 hospitals has 1,500 and 5 have 500. So these are simulating heterogeneous sample size across different hospitals. And the y-axis is biased to gold standard. Again, we use the pooled analysis as a gold standard. We study the relative bias of the meta-analysis approach, which is a very common and popular, and also the proposed ODAC approach. And we study this under different scenarios of event rates, 20%, 5%, 2%, and 1%. And it turns out that the meta-analysis is affected by the event rate quite dramatically. If we drop from 20% to 1%, there's a huge relative bias. And on the other hand, the ODAC algorithm is very stable across all the scenarios. So this is another application. So we use this ODAC algorithm to the Odyssey setting, and we have 4 databases. Again, for this case, we have we can physically pull all this data together. So we have a gold standard to compare with. So we study a particular population, and we study the outcome of AMI, which is a rare condition. And we fit a Cox regression model with 8 risk factors. And here are the results for AMI. So we have here we have 8 panels corresponding to 8 risk factors: age, alcohol dependence, gender, obesity, and type 2 diabetes. So we have 3 estimates: the pooled estimates, as well as the confidence interval. We also have the meta-analysis estimate, and also we have ODAC estimate. Okay. So as you can see here, overall, the ODAC estimate approximates the pooled estimate very well. They agree very well in almost all the situations. On the other hand, for some outcomes, the meta-analysis is quite different, and sometimes they don't even overlap in terms of the confidence interval. And in terms of scientific conclusion, like how much difference does it make? The answer is that it can actually make a huge difference. So if you take a look at this one, alcohol dependence, both distributed algorithm, ODAC, and the pooled estimate have confidence interval excluding 0, suggesting alcohol dependence is a statistically significant risk factor. But using meta-analysis, the conclusion is completely flipped. And for other things, it also we have the similar things happen here and happen here and here. So you can see 4 out of 8 risk factors. The conclusions are qualitatively, not only quantitatively different, but also qualitatively different. So this is suggesting that when we use meta-analysis for rare disease or rare exposures, we should be very cautious, and we should definitely consider the distributed algorithm, which has similar communication costs to meta-analysis. So now we talk about the two methods. Now let's offer some intuitions here. So this is actually a very nice intuition I learned when I presented this work in Hong Kong last year, and epidemiologists had a very nice observation to explain the idea. So basically, let's put this surrogate likelihood idea in the simplest possible setting. Say we only have one parameter. So when we only have one parameter, we can easily visualize the likelihood function, and the initial value beta bar is our is a maximum of likelihood function, right? So we know the slope would be flat at maximum. Now you are going to send this beta bar to other sites. You ask other sites to send the gradient back to you. So what is a gradient in one-dimensional case? It's simply the slope, right? So this is suggesting that if in the second site they get a negative slope, it's basically suggesting that the maximum of their likelihood function is on the left. So basically this site is voting to move this estimator to the left. And the third site is suggesting, which has a positive slope, is suggesting the maximum should be on the right. So it's voting to the right. So by using all the possible gradients together to augment, to modify the local likelihood function, it's basically idea is to build a consensus about where you should move this estimator, to the left or to the right. So this is the corrected shape of the likelihood function. So this is actually the simplest intuitive explanation of the surrogate likelihood function. So the next question is why this method is better than meta-analysis in some settings. So the meta-analysis is based on the point estimate and standard error. So that is the inference can be dependent on the asymptotic approximation. So you need a larger sample size, or the outcome cannot be very rare. On the other hand, this surrogate likelihood function is a likelihood-based inference. So even for those hospitals who have very few patients, you can still get a reasonable shape from those hospitals. So extreme scenario I can give you is that if at site 2 and 3 there is no event, so if you use meta-analysis, so to calculate the hazard ratio, or to calculate odds ratio in a 2x2 table, it would be difficult, right? So what do you do with this? Are you going to remove this site? If you're jobbing those sites, can also introduce bias, because no event from, say, 200 patients is also important information to be incorporated. Jobbing those 0 events is going to introduce bias. But on the other hand, if we, instead of using the point estimate and the standard error from meta-analysis, we use the likelihood-based inference. Even if you have no event, you still have a likelihood function to work with. So we can still incorporate those likelihood function to augment or correct the shape of the likelihood function. So that's the intuition why this surrogate likelihood work and why it's better than meta-analysis. Okay. So now we talk about the time to event analysis. We basically covered OLL 1, OLL 2, and ODEC. And what's next? So when we present these ideas to our collaborators at CHOP and Odyssey, from clinical point of view, many questions arises, and the primary question is really the heterogeneity, because almost all the methods I reviewed, we are talking about homogeneous data from different hospitals, but in reality, the patient characteristics, the intervention, the way people conduct the intervention, there are a huge amount of heterogeneity. at many levels. So the question is, how do we account for those heterogeneity? So if we revisit this idea from surrogate likelihood function, underlying assumption is that the local likelihood function should have similar shape with the combined likelihood function. So this way you can use the high order gradient from the local likelihood function to approximate the combined likelihood function. So that's the underlying assumption. So, but in heterogeneous case, this doesn't hold. So this leads to our new framework of heterogeneity aware distributed algorithms. So there are many ways to handle heterogeneity. So here we are exploring, one of the ways. In particular, we consider the case that we have a common parameter of interest across different hospitals, and we have a nuisance parameter, gamma j. This is the site-specific nuisance parameter to account for the between-site heterogeneity. So in this case, I think the fundamental challenge is that the local likelihood function will no longer take the same shape with the combined likelihood function. So the question is, how do we approximate it? So for the sake of time, I'm going to just talk about the general idea and ignore all the Greek letters. So the first thing we did is to change the target function to the combined efficient score function. So this way we can reduce the impact of the nuisance parameters. And second thing we did is to find a local function and define a new local function and construct a high order match. And the idea we use here is a density ratio tilting idea, and from this fundamental equation. Okay, so with these two techniques, and we are able to construct a new estimating function and a new algorithm for this distributed setting. So we actually have more than one step. Here we have two steps. We first need a local place, different hospitals to do their local estimation, send the result to a local site, and then we initialize the estimate, and then transfer intermediate result, and then send back local site to do the analysis. So here we do have one more communication compared to OLL and ODEC, but we think this is a reasonable step to take when we have heterogeneous data across different sites. So this one more step is really used to help us to account for the heterogeneity, calibrate the model. So we believe this is a necessary step. So theoretical investigation, we actually showed that the proposed estimator, again, will give you the identical efficiency as if you pull the data together. It's fully efficient. On the other hand, the meta-analysis is not fully efficient. So this paper is under revision at Biometrica, and it's also posted at arXiv. So if you search heterogeneity aware and communication efficient distributed inference, you can find this paper. Okay, I'm going to skip the numerical results, just talk about the some discussions and software. So in the past year, so we have also been working on making those our work accessible to others. So we developed this package called the PDA. It's a part of the product from our Pencil lab. So so we are distributing this our algorithms to ISNet, which is a pediatric learning health system led by CHOP, One Florida, and Odyssey. And some of the implementation challenges include, integrating our algorithms to different types of common data model, and also initiate those project implementations. And in addition to those dissemination tasks, we are also working on newer models. So there are different additional scenarios. For example, some hospitals may only have a list of, say, 20 predictors. The other hospital have another list of, say, 30 predictors. So those predictors may or may not fully overlap. So how do we handle those situations? So it's a block missing data problem. And also, we are also handling other models that can deal with heterogeneity, such as mixed effect model and generalized linear mixed effect models. And in addition to estimation and inference, we are also working on prediction. So in particular, we are borrowing ideas from transfer learning and federated learning. And from operation point of view, it's also important to quantify the heterogeneity before you integrate the data. So how to quantify the heterogeneity in this distributed data setting? And how do we handle different types of heterogeneity? Those are the questions we are working on right now. So finally, I want to thank our research team. So this is mostly from the dissertation work of my former student, Ray Duan. And she just started a week ago as an assistant professor of biostatistics at Harvard University. And also the rest of the group members working on this project, Mac, Chongliang, and Jesse, and also collaborators at UPenn, Odyssey, and One Florida, and Cornell University. So thank you very much. I'm ready for the questions.
Thank you so much, Dr. Chen. This was such a great presentation. I think I finally understood what's a distributed model. This is really great. Any question? So I'll start. I have a question related to when you do these distributed models. How do you handle missing data, from various sites and missing variables? Because I guess, not all the sites will have. I think you mentioned that, some sites may have not the same number of predictors, but also, within each predictor you will have a lot of missing data. So how does this? How do your models handle that?
Yeah, that's a great question. So there are two layers. One is structural missing. That's something we are still working on. And regarding the traditional missing data, as you said, say even if we have the same set of predictors, but we have all the we can have all the missing data, and the practical way to handle it is through this imputation. We use imputation to impute, and in addition to imputation, we can also model the missing data mechanism within each site.
Oh yeah, okay. So you will do it within each site, and
yeah,
then calculate the betas
yeah.
and all this.
We can model the propensity of the missingness. Sometimes the missingness can be very informative. For example, type 2 diabetes, and so only for type 2 diabetes, a very important measure is A1C glucose level. So, but this number, this glucose level, is only available in our data set. It's only available to 5% of the patients. So that means we have 95% of missingness. This is an non-traditional missing data. Typically, traditional missing data, we are talking about 20-30% of missing. So it turns out that for those situations, the missingness itself is a very strong predictor. So only typically those people who have high risk for having type 2 diabetes, those patients will be asked to do this to measure their glucose level. Right? So if those people who are not asked to measure this, they are typically at lower risk. So there are certain, this missing indicator itself is a very important, useful predictor to the outcome. So when we build a regression model or prediction model, so we do also consider those missing data pattern in the model building.
I see. Any other question? So I have questions. We could spend another hour.
Yeah.
So is this how a PicoNet works? I mean, have you had projects either with PicoNet or other projects with Odyssey where you suggest an analysis and then you run your model and then you ask them to run the same models and then they send you all the various information?
Yeah, this is we are working with especially working with PicoNet in the last few years, and more recently with One Florida. So we do have collaborations with PicoNet, and we use the PicoNet, particularly those two PicoNet funded consortium networks to help us validate our algorithm, because they do have the data centralized at one place. But it's not the case for many other settings. Many other settings, like this one, we recently started work with Vanderbilt. So for Star Network, it's formerly called the Mid-South, I think, Mid-South, and including UNC and Chicago, I think, Vanderbilt. So their data are distributedly stored. So they don't have data centralized at one place. So basically what we are doing is that we use those centralized research network to test, validate, and evaluate our method. And then we are extending our algorithms to those other settings, other consortia who do not have the data shared in one place. So that's the idea.
So, but I guess everyone needs to have the same common data model, right? I mean, so
yes.
that you can.
Yes.
So you have first to select the sites that have the same data model, common data model as you have.
Yes, I think those projects they were funded by PicoNet. They have the Picori common data model, and Odyssey they are also converting data to OMOP common data model. So they are. So I assume those infrastructure is already there, so that it's ready to test and evaluate our algorithms.
Right. It's great. Any other questions? All right. Well, if we don't have any other question, well, thank you so much. This was extremely informative and interesting for all of us. And,
Thank you.
Thank you again. And I'm sure we'll have we could start some collaborations.
Yes.
I have ideas.
Yeah, great. Yeah, look forward to that.
Okay, great. Thank you so much.
Thank you for having me.
Bye.
Bye-bye.